On the number line, it is very easy to see 5 is greater than 4. Even when the signs are different, like comparing -5 and 4, we can use absolute values to compare their magnitudes. The absolute value is just the distance between any number to the origin. But in 2 or higher dimensions, you cannot directly compare 2 vectors. Take 2 vectors like A 3 minus 4 and B 0, 5, which one is bigger? To make this comparison possible, we introduce something called a vector norm. Simply put, a vector norm gives us a way to measure how big the vector is. The vector norm maps a vector to a scalar based on a specific rule. Then we can use the scalars to measure how big vectors are. Let's start with L1 norm. The L1 norm adds up the absolute values of a vector's components. For example, the L1 norm of vector A is absolute value of 3 plus the absolute value of -4, which equals 7. And for vector B, its L1 norm is the absolute value of 0 plus the absolute value of 5, which gives us 5. So according to the L1 norm, vector A is larger. So for a 2D vector x, the L1 norm's contours in the plane are tilde squares. A contour is a curve or shape consisting of all points which are at the same distance from the origin under a given measure. The Altoorm norm comes from Pythagorean theorem. Square each component, add them up, and take the square root. It gives us the straight line distance from the tail to the vector's head. For vector A, square 3, you get 9, square -4, you get 16, add them up, that is 25. Then take the square root to 25, which gives you 5. That is the Altoorm norm of vector A. Very easy for vector B, its Altoorm norm is also 5. So by the Altoorm norm, vectors A and B are equal in size. The Altoorm norm's contour lines in the plane are perfect circles. The L infinity norm is also called the Chebyshev norm. It takes the largest absolute value among a vector's components. For vector A, take the absolute values, 3, 4, then pick the larger one, which means vector A's L infinity norm is 4. For vector B, its L infinity norm is 5. So under the L infinity norm, vector B is larger. And the contour lines of the L infinity norm in the plane are squares. To generalize these different norms, we define LP norm. As we can see for 2D vector x, as p increases from 1, its LP norm contour changes smoothly in shape. Now let's head into RGB space and look at norms of color vectors. In RGB space, vectors with L1 norm equal to 1 all end on a plane. With L2 norm equal to 1, the vectors and points lie on the surface of a unit sphere. With L infinity norm equal to 1, vectors' terminal points land on the 3 brightest faces of the RGB unit cube. You can use LP norm to measure the distance between any 2 points on a plane. But how do we store all these distant values? You're probably already thinking, a matrix. Matrices and operations on them, that's exactly what we'll dive into in the next chapter. See you then.